Hello, welcome to Cadence's booth at Embedded World 2024, where we're going to be talking to Markus from Dreamchip and Robert from Cadence, and we're going to be talking a real-life example where there's some machine learning going on, where we can take a 3D box like that from a 2D camera like that by using machine learning capability delivered by Cadence, so Dreamchip can make the chip that does just that. So Markus from Dreamchip, if you could just explain to us what's going on with this demo, and then we'll move over to Robert, who can explain the role that Cadence played in order to make all of that possible.
Yes, hello. Let me introduce the latest automotive SoC from Dreamchip.
Yep.
So maybe let's first start with the demo that we're seeing here. So we created this as a showcase to have something running on the chip that is the center of this one. So we trained, as you said, CNN to detect real 3D coordinates from just a 2D image, and of course for display it's going to be projected back to 2D. But let's dive deeper into the chip that we created.
So just to be clear, for the sake of this demo,
yes,
what's being created here in real time is just this one single camera.
Yes, we have a monocular camera, and the CNN infers the 3D coordinates of the bounding boxes, and then display, of course, projects them back to 2D.
Yeah,
exactly. So let's dive into the chip. There are several IP cores integrated into this chip. To start with, there are two ARM Cortex-A65 cores. In this demo, they run a Linux operating system, but of course, later on, they can run as well real-time operating systems. And the reason why we're at the Cadence booth is because we have integrated the Cadence NNA 110 AI accelerator, which does the actual inference. So this is the one that runs the CNN, and it also does some pre-processing, so color conversion and post-processing of the CNN, and it also draws the bounding boxes into the final image. As this is an automotive IC, we also have a safety island, which is built around two ARM Cortex-R52 cores, which run in dual-core lockstep. And the whole chip was fabricated by Global Foundries in their 22 FTX process. We've got 1.8 billion transistors on a 93 square millimeters chip, which gives us roughly 10 tera operations per second of AI performance.
And that's a lot of data.
Yes, it is.
That's a lot of data.
And I'm not yet done. So there's also our own IP cores in this one. So especially it's the low latency Dreamchip image signal processors. They're good for converting the raw data that was captured by the image sensor into the RGB data that we can see here.
Yeah. So just help the listeners understand what the relationship was between, because we're going to talk to Robin in a moment to talk about how Cadence do this kind of thing, but just explain to us the relationship that you have with Cadence, because obviously to make something that's doing that kind of machine learning, very, very clever. You've taught the machine to recognize the image and then turn it into a 3D box. So it's learned with millions and millions of images to create that box.
Yes.
So just explain for us the sort of head start that Cadence was able to give you with what was going on here, so that you didn't have to reinvent the wheel to create that. Just talk us through how that works.
Yes. So we, as I said, we do custom chip designs, and we use the Cadence IP in this case to have some powerful processing elements that we do not need to build ourselves. So we use, let's say, more or less off-the-shelf available processing elements that are optimized for AI performance.
Right. So when you're doing that, how much customization, once you take their files and their libraries to do what you've done, how much did you then have to do on top of that?
Well, for the CNN accelerator, it is fairly simple what we did. We just really used the ready-trained...
I'm sure it wasn't fairly simple, but anyway, it's very nice of you to say, Markus. Very good.
This part is actually rather simple compared to the other stuff. So the tools do the mapping of the CNN, which is trained in Python, and map this one into binary code that can be run on this core. So this is rather an automated process that the Cadence tools do. The complexity is rather in the rest of the chip design for us. So the work that we had to put in went into the other parts of the chip.
I see.
That's one of the main.
That's where it got complicated.
Yes.
That's where the clever stuff came in. Okay. So if we hand over to Robert now, who's from Cadence, we talk about AI all the time. You go around the embedded world, everybody tells you we have AI.
Yeah.
Sometimes you wonder, do they really have AI? Are they actually doing AI? So maybe you could explain to us the role that Cadence played to enable this machine learning example where you've taken millions of images from a camera to create a 3D box. How does Cadence go about doing that?
Yeah, so Cadence sure does have AI, a lot of AI, and so this is a digital chip. And first of all, so we've been partnering with Dream Chip for many years. And so for this chip design, they used our digital design flow RTL to GDS2, which you need to produce such a chip in GlobalFoundries 22 process technology. But for the AI part, you need a very specific tooling. So as Markus has explained, so they have used our Tensilica DSP along with our Tensilica AI accelerator. And you can work in different AI frameworks like PyTorch or Caffe and so. But the tooling helps our customers to automatically map the AI network to our Tensilica processor by using our XNNC compiler, AI compiler, that does the mapping on the target hardware platform. So that's how we both work together.
Yep.
In addition, because it takes quite some time until the chip is ready and is fabricated so that you have your first test samples available. And that's why Dream Chip did, together with Cadence, using the tool from us called Helium Virtual Studio, they created a virtual platform. So by having a virtual platform or digital twin of the chip, they could already start, before the silicon becomes available, with the software development on this virtual platform.
Right.
And once the chip comes back, they have already done most of the work and they just need to do the actual mapping of their software on this chip and test it.
So if I understand that correctly, there's sort of three parts to that stage then, isn't there? There's the libraries that enable the platform on which they're going to build their model and their machine learning. There's also, if you like, the production-ready platform that means that you, as Cadence, understand how you're going to take that to fabrication to actually build the chip so that you know that it works. But then you have this virtual environment that ensures that they also understand what they've designed is going to be manufacturable and will work.
Yes.
So it's not just, so if anybody thinks, oh, Cadence just help people design chips, there's much more complexity to it than just that.
Yes, there is. So actually, the Tensilica tool environment called Explorer allows customers, first of all, to configure the processor exactly towards their needs.
Thanks.
And then, in order to build a virtual platform, once you've configured our processor and our AI accelerator, you need to push a button to generate a System C model for your virtual platform. So that means we have a library in this tool environment in Helium for all our processors so that you can use it to build a virtual platform. And that's what exactly Dream Chip did.
Right. So from Dream Chip's point of view, Markus, having the ability to sort of be absolutely, I mean, there's an absolute assurance to understand that when you dream something up, being Dream Chip, forgive the pun, when you dream something up and say, I want to design a chip, you go to Cadence, they don't just give you the files that will give you the platform on which all your dreams are going to come true, but they also give you the ability to know that you can manufacture and then also understand in this virtual world where you can actually see it working and what happens in order to make the chip actually happen.
And that's why our collaboration works so great, because our claim of fame is, as you can see here on the wall, unleash imagination, and then Dream Chip comes and make dreams come true.
Where's Walt Disney when you need him? Okay, very good. So that's a really so for embedded engineers everywhere who have to meet up with people like Markus, who will go and buy his chip, who will trust him to deliver a chip that they're going to put into their systems. Actually, in fact, what's going on is this absolutely insurance program from Cadence that ensures that you can make it, it will work, we've tested it.
Yeah, and let me add one more thing. So we have now this working silicon here at our booth, but there is DreamChip works already on the next stream. It's a much more powerful chip that has even 8 more processors from Cadence, Tensilica processors on this chip, and the chip will tape out in June. And this one is then really perfectly suited as a starting point for a customer for an autonomous driving platform. And if they need a strong IC partner like DreamChip to make this dream come true on silicon, then they can talk to us.
Yeah. So I think that what's actually really wonderful about this discussion that we've had is we're at Embedded World, and design engineers around the world need to know that when they get a chip, they don't necessarily have to understand everything that goes on in order for that to happen. So this is a really good introduction for them to understand the relationship between the chip manufacturer, the IP deliverer, and everything that goes in the ecosystem.
And all the EDA tools.
All the tools, everything that goes into the system to make sure that when he sells a chip, it works.
Yeah.
Very good.
So our goal is to enable our customers like DreamChip, and they help their customers to create the silicon.
Very good.
Yeah.
Robert, thank you very much.
Thanks for
Markus,
having us.
Thank you very much.
Hey, yo, where my engineers at?